hole is a region of space that is so dense, there's so much gravity that nothing, not even light, can escape. We see these supernovas all the time. They're some of the brightest objects in the universe. Sometimes a supernova can be brighter than the entire galaxy. That's it's inside.
In the last throes of a very massive star's life, increasingly frantic fusion in the interior produces one periodic table element after another. That finally surround an iron core. The formation of that core represents the end of exothermic fusion. Fusing two iron nuclei absorbs energy, it doesn't release it. So, starved of an energy source, the stellar core collapses on itself. Electrons are slammed into protons in the iron nuclei, forging a neutron star. The space-time curvature at the neutron star's surface is pretty extreme. Clocks run noticeably slower, and the densities inside the star produce some very strange states of matter.
Surrounded this region where if you fall in, it's called the event horizon. When you go across that horizon, then you are going to the centre. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip.
Singularity is a point of infinite gravity where space and time become meaningless.
The Schwarzschild radius is the distance from the center of a black hole below which nothing, not even light, can escape. The heavier the black hole, the bigger the Schwarzschild radius. But when supergiant stars die, their supernova explosions are so powerful they can compress the star's already dense cores past their Schwarzschild tipping points to become black holes.
Mass is relatively easy to determine. far away from a black hole, you can even use Newtonian physics. By measuring the gravitational effects of the black hole on other bodies, you can estimate the mass of the black hole. But spin is harder to measure because, unlike mass, it only affects objects relatively close to the black hole. Here, there is an innermost stable circular orbit, with a radius known as r ISCO. Closer than this, and no orbits are stable. They all fall into the black hole. What's useful for our purposes is that r ISCO depends on the spin of the black hole. The faster it's spinning, the smaller r ISCO becomes, assuming it's spinning in the same direction as the matter in the accretion disk.
When a black hole reaches about 230 metric tons, it'll have only one more second to live. In that final second, its event horizon becomes increasingly tiny until finally releasing all of its energy back into the universe. And while Hawking radiation has never been directly observed, some scientists believe that certain gamma-ray flashes detected in the sky are actually traces of the last moments of small primordial black holes formed at the dawn of time